distributions. And in the earlier session, so these are all the sessions that we have had. In session 1, we discussed the importance of statistics. Session 2, we covered center and spread of the data, covering mean, median, IQR and all. Session 3, we had probability. Session 4, we covered the conditional probability and random variables. And in session 5, the last session, we covered random variables, and we started the discussion on the two distributions. We wanted to see uh, discrete and continuous distributions, and we talked about the Bernoulli trials and the binary random variable. So today's session will continue this and will focus on the normal distribution. We'll also have a working example. We have an Excel example, a number example basically, to see how our binomial distribution graphs look like. Right. So just to recap again, in the last session we discussed Bernoulli trials. For Bernoulli trials, what are the Bernoulli trials? They have these three properties. The result of each trial, it can be a success or a failure. There are just two outcomes. There is nothing in between. It will be a success or a failure. The second is that the probability of a success, it has to be same in every trial. The third is the trials have to be independent. Okay. Next thing we discussed the binomial random variable. So the random variable for this Bernoulli trials, it converts to a binomial random variable. And then we saw the distribution, the probability distribution for this binomial for Bernoulli trials and the binomial random variable. So the probability of k successes is given by this formula NCK, where this is the representation for NCK. This means N choose K. This is the same as if you remember the formula in the combinations, permutations, combinations, NCK. This is the same formula, okay? Into P raised to the power K into 1 minus P raised to the power N minus K. So N is the total number of trials and K are the number of successes that we want, right? So this is what we saw in the last sessions. Moreover, just a continuation, the NCK, this representation means NCK, and this is n factorial divided by k factorial into n minus k factorial, where so and so on. This is an example. 4C2, it would mean 4 factorial upon 2 factorial, 2 factorial. It would give us a result of 6. So 4C2 means choosing 2 out of 4. That is what it means. 4C2, 4 choose 2. So out of 4 things, we are choosing 2 at once. What are the number of ways in we can choose it? So this 6, what does it represent? It represents the number of ways in which I can choose 2 amongst these 4. Okay, I can either pick AB, I can either pick AC, AD, BC, BD, and CD. These are the number of total ways in which I can pick up 2 values from these. Now, let's say that we have a P of 0.5, right? And for a P of 0.5, what is the binomial probability distribution? Let's see. Now, from the earlier formula, we already know that the probability is equal to NCK into P to the power K, 1 minus P to the power N minus K. Okay. Now here, when they say K heads, so again, let me repeat the experiment. It is 6 coin flips. So 6 times you are going to flip a coin, and then K is a number of heads. Okay. So in this experiment, we are trying to prepare a table where the number of heads are 0, 1, 2, 3, 4, and 5, 5 and 6. Okay. Now the probability of getting 0 heads, basically 0 heads meaning in all the 6 coin flips you have no head, right? So the probability, you can go back to the formula or you can deduce it by reasoning also. I would suggest you go back to the formula because that is what you should ideally do. So NCK into P to the power 1 or P to the power K. So K here is 0. So P P is 0.5. So, or we can call it as 1 by 2 also, right? And into 1 minus P to the power n minus K, right? 1 minus P is 1 by 2. So, again, the same thing. So, this will be your probability of 0, right? This formula, this one. This is the formula that we are talking about, okay? And similarly, if you check it for all the case, these are the probabilities that you will obtain. Now, if we plot this, then this is what we see. This is a histogram. Okay. Now, in the later part of the discussion, what we will see is that how this histogram is important and how it approximates to a normal distribution. Again, if we go back to the Demier's role of four dice, so if you remember, there was an experiment discussed in the initial sessions where this guy Demier, he's a gambler, and he was placing his bet on the number of sixes that would obtain in 24 rolls of four dice, right? So for that particular example, uh, I would say it's a homework that you need to find out the distribution, okay, for the number of sixes. If the number of sixes are zero, the probability is 625 upon 1296. If it is one, it's 500, and this reduces drastically if you go on to four sixes. It's 1 by 1296. Okay, so this is a homework. Moving on. The mean, let's talk about the mean and the variance of binomial distribution. uh, Binomial distribution, let's say the probability of a success is p, small p, then, and n is the number of trials, then the expectation or the mean mu is going to be np, and the standard deviation square, so basically variance, is going to be np into 1 minus p, right? So also, if you want to derive it from a intuitive sense, then you can see that the expected if you are throwing a coin, let's say a coin or a success event, you are doing it n times. The expected number of successes has to be np because you are repeating it n times. So it would be p into p into p into p, right? So that will be your cumulative thing, right? It would get multiplied everywhere. So similarly, if you see that the variance, it also follows from the fact that the binomial is the sum of n independent Bernoulli trials of variance p into 1 minus p. Okay. So you can also calculate them intuitively, but if you remember them for a binomial distribution, that would be easier for you. Now let's see. So we have a working example. Okay. Before that, let me explain what we have here. Okay. So if you talk, so this is a table where you have the values of probability where x is equal to k. K is the number of successes. So let's say your n is equal to 10, and for that k can be anywhere ranging from 0 to 10. Okay, you can have zero successes, you can have one success, two success, three success, and so on till 10 successes, right? Now, what will be different? Your P can be different. For example, if we toss a coin, in that case, P, probability of success is 0.5. But there can be other experiments as well. Let's say where your probability of success is 0.1. So in that case, what are going to be the probabilities of having, uh, you know, zero successes, one success, and so on? So if you see this table, I mean, intuitively, it also makes sense because um, if your probability is 0.1, so then the probability of having zero successes is 0.34. So 34% chances are there that you won't see any success in the 10 trials, right? But if your probability is zero point 0.9, so that means it's a highly likely thing. So your probability of getting 10 successes is 0.349, right? So we'll see how can we drive it. Yeah, so let's go to the sheet. Okay. So in this we have, let's say the n is 10, as I already discussed, and let's say the values of k can vary from 0 to 10 in this case, and nck, that factor of nck, it will be 1 if k is 0, and so on. I mean, you can just use a formula as well. You can derive it mathematically as well. It's just n factorial upon k factorial into p n minus k factorial. So these are the coefficients that you will get for 10 ck basically, because n is 10 here. Now, once you have these, once you have these coefficients, then what you will do is you will get that, you will prepare this table. This is the same table as this table, okay? And how you get this table is this factor nck into this power function. It's just for raising any number to some power. So I have just used b7 and raised it to the power of k into 1 minus p to the power n minus k. So that's it. So that's the only thing that I've done. So now probability, in this sense, you will calculate the probability for everything. Okay. Now once you have the probability of it, let me enter here 0.1. So now what you see here is these values, these 0.349 so on, plotted in the graph in a bar chart basically. So what it means is that for a k of 0, the probability is almost 3.4, and the maximum probability is having one success, which is this. Okay, this is a like 0.387. Now let's try changing the value of p and see how this graph looks. Okay, so if you change it to, right now it is 0.1. If I change it to 0.2, what happens? Just observe it. We'll talk about it later. Now zero point 0.3, now zero point 0.4, now zero point 0.5. So this case is special as it relates to the coin tossing thing. Okay. So if I talk about the exact values, these are the exact values. What it means is, if I toss a coin 10 times, then the probability of getting 0 heads is 0.01, 1 heads is 0.01, 2 heads is 0.04, and so on. And the maximum probability that we get is 0.246, which is getting 5 heads, right? So next time, if you, let's say if you have a bet on, okay, how many, if I am conducting, if I am tossing a coin 10 times, what should I bet on? So you should definitely bet on getting 5 heads or 5 tails, because that has the most probability, like the highest probability, right? Now let's move on to more to other events which have higher probability for success. Let's say zero point 0.6, and then zero point 0.7, and then zero point 0.9. So what we see that the highest probability is shifting, right? Because the value of p is different, right? So that is expected. So that is one thing, as I was already mentioning, right? So depending on the value of p, your expected probability would vary. I mean, the probability of getting a k number of successes would be different. Okay. Now, from here, let's see how we can, let me change it back to 0.5. Okay. So this is a very beautiful graph. Why? One is it is symmetrical. Okay. This is the midpoint, and this right half and this left half are pretty symmetrical. Okay. So that is one. Now let's see how we will translate this graph to other things. Okay, so we have already discussed about the graph. Let's move on. Now we did it for n is equal to 10, but back when there were no calculators, no Excel sheets, and all, doing these things for very large values of n, it would be a pain, right? So what James Bernoulli did and Abraham de Moivre did, they tried to solve it without using a computer. So I mean, that time calculus was also in very initial stages, right? So then he observed that the binomial distribution was closely approximated by a continuous density function, and we could define that function very simply, right? Now let's see how this works with the p is equal to zero point 0.5 and n is very large, right? So this distribution is going to look something like this. Okay, if n is very large, the distributions that we saw earlier in the Excel sheet, they are going to be, I mean, you will see them, you will see the probability distribution graph as this. Now let's say n is sufficient enough to do approximation. So what you do is, so what he did is, do me where he split the graph so that the mean is zero. So we, as we had, we have already observed that the graph is symmetrical. Okay, so what he did was just he slided the axis and gathering on the experimentations that he has observed and that he could do for large x, for large n, is what he was trying to do. So he slided the y-axis. I mean, you can slide the y-axis well as well. It's the same thing. And he also tried to squash the curve along the x-axis. Squash, so meaning pushing the curve towards the y-axis from both sides at once, right? So the area under the curve, it has to be, again, it has to be the sum of probabilities. So it has to be one. So that's why we have to squish it. Okay. So once when we do it right, then we obtain a very beautiful curve like this, which is the standard normal distribution. Okay. And the equation for a standard normal distribution is this: fz is equal to 1 upon under root 2 pi into e raised to the power minus z square by 2. So this is the equation for the probability density of a random, of a normal distribution. And e is the same constant that we have, the value is approximately equal to 2.718. Okay. We'll talk more about this. Now, if I talk about this equation, the standard normal equation, so mathematically, you can also see what you can just integrate it and see what is the mu, what is the standard deviation, and what you will observe is that for a standard normal distribution, your mean will be 0 and your standard deviation will be 1, which means the variance will also be 1, right? Moreover, it is symmetrical. It is symmetrical because fz is equal to f minus z, and a maximum occurs at z is equal to 0. And how you can see the maximum? You can just equate the derivative to 0 and then find out the value of z. So for this particular distribution, the maximum occurs at z is equal to 0. The area under the curve is 1. It is symmetrical, and the standard deviation also comes out to be 1 in this case, right? Now why do we call this standard? Because this has very simple properties, right? So that's why we call it standard normal distribution. We will see again how we can convert any distribution to a standard normal distribution. Now the other normal distributions which are existing in nature or around us, let's say they have a mean and a different variance. For a standard normal distribution, we know that the mean is 0 and the standard deviation is 1. So let's say if we have some other curve or some other data where the mean and the variances are different, right? So we can modify the formula here for those distributions, and it will modify to fx given mu and sigma. Given mu and sigma meaning, so this is for the probability density function for the normal curve or a normal distribution having a mean of mu and a standard deviation of sigma. So that probability distribution is given by, or density distribution is given by 1 upon sigma under root 2 pi into e to the power minus 1 by 2. So we had z square, right? So instead of z, we get x minus mu by sigma. Okay, and we get a sigma in the outer part. So again, if we plot this, right, it will again give me a symmetric distribution, and it will be a bell shaped. The center will be mu, that is the mean, and the standard deviation will be sigma. So you can, from this density function, you can calculate the mu and the sigma. And once you do it using integration, you will get a mean of mu and a standard deviation of sigma. You can try this. Moving on. So here we are talking about, let's say, two curves. Okay. In one curve, let's talk about this curve. Okay. Here we have a large sigma, right? So sigma is large, and here we have a small sigma, right? So what would happen is the area under the graph, it has to be 1. Okay. So if your sigma, which is the distance from here to here, if your sigma has to be large, then your graph, your peak of the graph have to be lower. And if the sigma is a small, then it has to be above. It has to be upper. Okay. So I mean, you can take them as standard things. And if you are given, let's say, standard curves or probability density functions, then from the plot itself you can say that, okay, for this curve we have a very large standard deviation, and for this curve we have a small standard deviation. Moving on. Now, so Demuir, he had proved it that the standard normal fits the binomial with p is equal to zero point 0.5 for a very large value of n. But it actually works for any value of p. Okay. So, does it mean that all binomials turn into normals eventually? Let's see. Generally, for any value of p, the binomial distribution of n trials with probability p is approximated by a normal curve. Okay. So, what we can say is, if you remember when were discussing the Excel sheet, we saw the distribution there. It was very close to a normal shaped curve, a bell curve. So that is what they're saying. That experiment can also be approximated by a normal curve with with mean is equal to np and sigma is equal to np into 1 minus p, right? So that's how we can correlate the binomial distribution to a standard normal distribution. Now, if you remember the D movier's problem, so there it was not looking very good. But do you think that it is also going to be a binomial? I mean, will this be normals? Right? Will this come under a normal distribution? So I would like you to think on that. Basically, right? We have already covered the wide range and higher sigma and lower sigma. So if you want, you can also think about this. Will it also fall under the normal curve, or will it be a part of the normal curve? Right now, as n gets large, the binomial distribution asymmetry is overwhelmed. When you say overwhelmed, what you mean is, um, I mean, you can see the similarity once you start increasing n, and let's say p is the same. So let's say the left hand graph is for n is equal to 2 and p is equal to 0.3. So what you will observe is, you will observe these, the bars that are there, and let's say these are the probabilities that you have observed. Okay. Now if you estimate, if you try to approximate it with a normal distribution, the normal distribution would be something like this. But once your n increases, if you increase the number of trials, let's say to 20, so these bars, these are the probabilities, the revised probabilities that you will see. Now for the same thing, the normal distribution would be this graph, the smooth graph, right? So this is very close to actual probabilities in case of n is equal to 20, but in case of n is equal to 2, it's very far away. So what we deduce is that as n increases, the binomial distribution, it approximates to a standard normal distribution. Sorry, not a standard normal distribution, but a normal distribution, because in here the mean is not zero. The mean is this value, something somewhere between 0 and 1. Moreover, I mean, this discovery that he had made, it's a special case of a very generic result, right? Which is the center limit theorem. So, since it's a special case, so we call it fuzzy center limit theorem, right? And that says that data which is influenced by many small and unrelated random effects are approximately randomly distributed. Sorry, normally distributed. So what they are trying to say is, when we are flipping a coin, if taking an example of flipping a coin, when we are flipping a coin, so the data that we get is influenced by many small and unrelated random effects. So it is going to be approximately normally distributed, right? So that is the conclusion the this guy team over came at. Now let's move on to the Z transformation, okay, of any distribution. Now, let's say we have a distribution where the mean is mu and standard deviation is sigma. In that case, we define a variable called z, and z is equal to x minus mu by sigma. Say this is the probability distribution for x having mu at having mean at mu, and sigma is that standard deviation. Okay, so these are the limits of one standard deviation, one above, one below. Now, once we do a z transformation, it transforms to another graph whose mean will be 0 and the standard deviation would be 1. So it would be 1 here, 1 here, minus 1, 2, 1. So this is the z transformation. Okay. So again, x is a random variable, and you apply the mean and standard deviation on it, and you get another random variable x. Okay. If you go back to the expectation formulas, you can have a linearity. You have a linearity in some of this combination. So you can apply them and see that the expectation of z is going to be 0. Now, moreover, once we have done a z transformation, right, we can we can find out a chart where we have the uh, corresponding to different z values. We can have the probability values. Okay, so this is the table which represents the various values of fz corresponding to the z. Okay. So in this graph, if you see, so this 0.5 probability observed for 0. Okay, so fz would mean the total area under the curve. Okay, and probability of fz, or probability of getting a z less than or equal to some constant value a, it would be fa, right? So you can see that probability of getting if you talk about this value, probability of getting z of less than or equal to a is 0.994, right? So z less than or equal to 2.5, the probability is going to be 0.994. So these are some very generic results that you will be able to apply on most of you will be able to apply on all normal distributions. And if you remember this graph, or at least some of the values from it, you should be able to see what is the probability of getting the values between one standard deviation, two standard deviation, and so on. So this is a very famous practice. This is a very popular practice once we do outlier correction. And uh, I mean, the some of the derivations here that we have, let's say if you talk about one standard deviation, it is 0.159 here and 0.997 here, 977 here. So once you subtract them, you will get almost like I think 82%, 0.977, and this one 0.1, 0.87. Yeah, almost 82%. Sorry, it should be 841. 841 and 159 is 7470. Yeah, almost 68%. So if you subtract these values 0.841 and 0.159, you will get the area between uh, one standard deviations, basically mu plus sigma and mu minus sigma, and it would be around 68% of the total area. So the probability is 68% to have the value between one standard deviation above or below the mean value. Let's see. Moreover, uh, let's say the left side is the graph that you have. Okay, the since you have done a z transformation, so the mean is 0, and let's say you have some value of a. Now the area fa would mean probability of getting a value lesser than or equal to a. So this area is going to be the probability. Okay. Now we can also graph the curve y is equal to fz, and the cumulative probability is going to look like this. This right chart is the cumulative probability of the normal distribution curve, z distribution basically. So this is the curve that you will get if you calculate the cumulative probability. Moving on. Now let's say from the table that we already know that if we want to get the probability of number lesser than a, this is the area. And if we want to get the probability of number lesser than b, then this is the area. So the probability, I mean, with some deduction, it is obvious that the probability of getting a number between a and b is going to be b minus a. Okay, so basically this area. So that is what they're saying here. Probability of z between b and a is going to be fb minus fa. Okay, and that's how we have it. The same example that I was talking about, that's how we have it for one standard deviation. So if you see, probability of getting a z between 1 and a minus 1 is f of 1 minus f of minus 1. You can go back to the f tables for this, but f1 is 0.8413, f minus 1 is 0.15, and this probability comes out to be 0.6826. So which means that the probability of getting a z value between minus 1 and 1 is 0.68 or 68%. Also, if you do if you calculate the probability of getting a z value greater than or equal to 2, it would come out to be 0.02. So you have 2% chances that the z value for a particular distribution is going to be greater than 2. Now, I mean, you can use this substitution x minus mu upon sigma, and you can use the table also to find the probabilities for other normal distribution. Let's see how. Okay, so as an example, let's pick up some student weights, right? Let's say we have picked up a data for the student weights, and we try to see the distribution. Now when we plot it, we see that it's normally distributed, and the mean is 150 with a standard deviation of 20. So the measurement unit is pound here for weight. Okay, now this is the curve that they follow, and the mean is 150 and the standard deviation is 170 and 130. Sorry, and the standard deviation is 20. So your upper value mu plus sigma, it would become 150 plus 20, which is 170, and this lower value would become mu minus sigma, that is 150 minus 130 is equal to minus 20 is equal to 130, right? So what is the probability of weighing more than 170 pounds? Now what they want to ask is, what is the probability that the students that some student is weighing greater than 170 pounds. So they are asking for this area. Okay. Now, from the previous discussion, I mean, from the thing that we already talked about in last couple of slides, the we already know the for the f value till this point, and for the whole graph it has to be 1. So let's see how we can calculate it. Probability of getting a x value greater than 170, we do as a transformation. We see x minus mu upon sigma greater than 170 minus 150 upon 20, and then it becomes as probability of getting z score greater than 20 by 20, that is probability z greater than 1. Okay. Now which automatically is 1 minus f1. Okay. So this the area up till here is 1 f1. Okay, and this area becomes 1 minus f1. So we know the value of f1, it is 0.8413. So when we do 1 minus f1, it is 0.1587. So the probability becomes 0.1587 for this, which means that the probability of having student weighing more than 170 is 0.15. Or we can say that a little less than one student in six tips the scales above 170 pounds, because if you convert it to fractions, right, it will be approximately 1 by 6. So that is why they are making this statement. So we have a little less than one student in six tips, they will weigh above 170 pounds, right? Again, a general rule for computing normal probabilities is, if you want to have a probability of x less than equal to b less than greater than equal to a, you have to calculate the f score for b minus mu upon sigma minus f score for a minus mu by sigma, and then you will have this probability. So I will conclude this session here. I think we should kind of practice on this one, how the f distributions are used and how we can use them. And I mean, if you want, you can try the normal distribution as well, the derivation as well. That will get a bit of more clarity. So yeah, I think, yeah, that was it for today.
Hello.